Honestly, I do. My test is what brings me up. Really? Yeah. I'm really good at that. I'm always good. I got second place at region for the series. I did the
All right, today is going to be very short because we have shortened periods, I think like 35 minutes or so. And then the rest of the day you have the half-hour lunches and periods, and then we have that drill. So I think this is going to be an easy day in my opinion. We're going to start the unit 2, and I think we're really going to like this section. You know how last year we spent a lot of time on derivatives? We talked about product rule, quotient rule, chain rule, power rule, all those things. And we really didn't get to integration, okay, working backwards, until like the last 2 months or so. And we've only discussed 2 ways to find an antiderivative, that kind of reverse power rule and U substitution. So we've discussed more ways to find derivatives than integrals. What we really focus on in Calc 2 now is to build up our anti-differentiation skills. So we're going to talk about how can we undo the product rule, how can we undo the chain rule. Okay, we're going to learn more skills to work backwards. Okay, because in Calc 1 you found derivatives, kind of working forwards. Does that make sense? Okay, so chapter 2 is all about integration techniques, okay, antiderivative working backwards. Our first technique we're going to talk about today is integration by parts. So I want you to take a look at the integral at the top of the page. You have x squared times sine of x. And if you really focus on this, it doesn't really fit either of the 2 anti-differentiation techniques that we know. Okay, if it was just x squared, we could do the reverse power rule for that. If it was just sine of x, we could use a trig antiderivative to help us with that. But we have both of them together being multiplied. So it doesn't fit the reverse power rule, it doesn't fit U sub. How can we still work backwards from it? Okay, so we're going to talk about how we can work backwards from multiplication. So if you take a look at this kind of bolded statement right there, this is kind of the key idea or things to look for to kind of clue you in to using this integration by parts technique that we're eventually going to cover. We have 2 factors, aka being multiplied together. Okay, factor means multiply. We know how to differentiate one or both of them. Could you find the derivative of just x squared? Yes. Could you find the derivative of just sine of x? Yes. So you know how to find the derivative of at least one of them. You also know how to integrate at least one of them. Could you work backwards from x squared? I think so. Could you work backwards from sine of x? Okay, so notice how you have that mixture. You can find the derivative of at least one, but you can also integrate at least one. If it fits that pattern and we're multiplying them together, we're going to try to use integration by parts. And the little formula that we're going to use for that is in this box. I'm going to eventually show you kind of where that comes from, okay, why it undoes multiplication or that product rule. But first, let's check out this example. So if you take a look at the box formula for integration by parts, you see those u's and v's in there. Okay, kind of like u substitution, how you let something represent a u variable. We're going to do that idea here, but we're going to do it kind of twice. We're going to let something be u, and we're going to let something be v. And I always want you to think about detail. What's it called when you take like the first letter of different words and you make a new word out of that? Is that an anagram? No? I'm not an English person. Acronym? Acronym? Anagram? I don't know. One of the two. Anyway, we're going to take this word detail, and each letter represents something different that we should be kind of looking for in these integrals that we're trying to work backwards from. Okay, so in the integration by parts formula, the first integral on the left-hand side, okay, this integral of u dv is your starting integral, okay, basically the one that the question or problem is representing. And we're going to take that integral and rewrite it as the right-hand side. So if this is our starting integral, we have to identify what do we want to let u be and what do we want to let dv be. We have those two different pieces. So this acronym, anagram, whatever we can decide on, detail, is going to give us a way to determine what we should let dv represent. And whatever we let dv represent, everything else is what the u should be in this starting integral. Okay, it might not be clicking in right now, but when we go through some examples, I'm hoping it does. Okay, so the way we choose dv is specifically through these other letters that represent the names or types of functions. Can you think of a type of function that starts with E? Exponential. Okay, so that's like a number to a power. What do you think the T stands for? A type of function that starts with T? Trig. Yep. So sine, cosine, tangent, those ones. What about A? Good. Have you done this before?
Yes.
Yes, you have. Okay.
Well, not the detail.
Not the detail. You've done integration by parts. Okay. So algebraic, those are like your polynomials, x to the third, x to the fourth, x to the fifth, anything like that. They could also be your constants. Maybe you have a constant value of like 5 or 4 or some multiplier out front. The algebraic could also represent the dx portion, because technically that's a constant of 1 out front. So algebraic, you kind of have a multitude of options there. It could be a polynomial, a constant, or that change in x. What about I? Specifically, inverse trig. So that would be your arc sine, your arc cosine, arc tangent. Okay. And the name of a function that starts with L? Logs. Logs. Okay, so this method, acronym, anagram, whatever, detail, is going to give us a way to specifically choose dv. So we first want to look for any exponential function. If we don't have an exponential, we're going to move on to trig. If we don't have a trig, we'll move on to algebraic, and so on and so forth. Okay? So taking a look at our first example here, what should we label as dv? Do we have an exponential in there somewhere? A number to a power? No. Do we have a trig in there somewhere? Yes. So we're going to let dv be cosine of x, which means the u variable, okay, so we already figured out dv, which means the u variable is everything else that we haven't labeled yet. So the x and also the dx. Well, actually, we'll let the dx be on the cosine of x. So we'll say cosine of x is dv, and then the x part will be u. Okay? So when we have these two things showing up here, you can integrate at least one of them, you can differentiate at least one of them. We're actually going to go through that down here. Whatever you label as dv, we're going to work backwards from that. Because if you work backwards from dv, what would you be left with? So, okay, think about it as 1 dv. If you work backwards from 1, what did you have before that? What could you take the derivative of that would give you just 1? 1v, okay? Or just v. And if you work backwards from cosine, you have sine. Okay? Whatever you let u be, that's what we're going to take the derivative of. So if you take the derivative of u, that would be du, derivative of u, over dx if you want to write that. And then the derivative of x is just 1, right? Okay. So by choosing dv and u in the starting interval, or integral, notice how we need to figure out v and du because those variables or quantities are showing up on the other side of that equal sign in the formula. Okay? So what we're going to do is we're going to say this integral is the same as, and we're going to fill in the other side of that equal sign with the antiderivative that we found and the derivative that we found appropriately. So we then need to figure out what is u. We'd label that as x. We need to multiply that by v. Notice how we found that to be sine when we worked backwards from dv. And then we have to subtract the integral of v, which we said was sine. And then we need du. But notice how we have du over dx equals 1. So can we solve for du? Multiply the dx over. Okay. So du in this case is just dx. So what this by parts does is it turns an integral where you're multiplying two different types of functions together into a new integral that you should be easily able to evaluate or work backwards from. So what is the antiderivative of sine? Can we work backwards from that? What did you have before sine? Yeah. Negative cosine, and if we were subtracting that, it would change to a plus. We don't know the bounds, so we need the plus c. So there's our first integration by parts. It's called by parts because you are literally breaking up the original integral into parts, okay, like a v part and a u part, and we're going to use those different parts or pieces appropriately in that little formula to help us work backwards. What's nice about these is if this is an antiderivative, you should be able to take the derivative of this and get your original one back. So you should always be able to check your work if you're not that sure. Okay, so you'd have to go through a product rule here to eventually do that, but if you checked it, you would get this original one back. Okay, so it's all about this formula. We're going to have to identify what is dv, what is u. We'll then have to work backwards from dv, find the derivative of u to help us fill in the other side of that formula. Okay, so I want to show you where this integration by parts formula comes from. Okay, so essentially, why does this work? If we're multiplying two things together in an integral, okay, you can also think about how we were originally perhaps multiplying two things together before we found a derivative. And if you're multiplying two things together, you would eventually want to use the product rule, right? Okay, so let's go ahead and say hypothetically, we are multiplying together u and v, and we want to take the derivative with respect to x of those two different functions, those two different expressions. Do we remember our product rule? Mm-hmm. Okay, good. Do we remember, I don't know if you've ever heard my phrase. Do we remember the phrase from last year for product rule? That's quotient.
Sorry.
Yeah.
1d2 plus 2d1.
1d2 plus 2d1. Okay, so you take your first function times the derivative of the second, which would be dv. 1d2 plus 2, and then d1. The derivative of u would just be du. Okay, so we're multiplying two things together and we found the derivative. In these examples, we want to do an antiderivative, meaning we're going to work backwards. So let's go ahead and see what happens. If we work backwards from both sides, if you take the derivative, or sorry, if you take the integral of a derivative, what are you left with? Whatever you started with, okay? Whatever it is, whatever originally was with respect to time or x or whatever the independent variable was. So we understand that a derivative and an integral are inverses. They kind of cancel each other out. So you're just left with whatever you started with. On the other side, if you're taking the integral of both of these, you can use a property of integrals very similar to distribution, where you integrate each one individually. Do you kind of see our formula in the box at the top kind of taking shape a little bit? Okay. So if you take a look in the box, the integral of u dv is solved for. Okay, it's all by itself, which would represent that integral. So if we want to get this integral by itself, we would have to subtract this one over. So uv minus the integral of v du. Okay, so that's where our by parts formula comes from. We're originally taking the derivative of two things being multiplied together, but now we are working backwards. Okay, we are integrating. So we're essentially undoing the product rule. Yeah?
Why do you solve for the udv one instead of the v? Like what made them decide to?
Like why solve for this one and not this one?
Because they felt like it?
To be honest, I don't know. I mean, it would be a very similar format, right? We would just have to figure out what would du be, and then the rest would be v. To be honest, I don't know.
So it's probably just different. Wouldn't it be like the same thing either way? You just like
It'd be the same thing either way. Yeah,
we
we would find du, but I don't know if we'd be able to use this detail process to help us. Okay, but that's a very good question. Why did they choose that one and not that one? I might have to look into it. Okay? So that's where it comes from. We are undoing a product rule. We are undoing derivative multiplication. Let's go ahead and check out some more examples on the back. We're just going to get used to identifying what should dv be, what should u be, and then using that by parts formula to help us work backwards. Okay, so take a look at this one. Think about what should dv represent. Okay, think detail. E is our first one to consider. Do we have an exponential in there? A number to a power? Yep, that would be e to the 4x, which means the other function you didn't choose is the u variable, which would be 2x. So we're going to work backwards from dv. That way we can figure out what v is. And we're going to take the derivative of u to figure out what du is, because those other parts show up in our formula. So if we work backwards from e to the 4x, can you think about what we had previously? Yeah. E to the 4x over 4. Yep. Maybe you want to write that as a 1/4 coefficient out front. That would work as well. Either one works well for that. And if you then take the derivative of 2x, we'd just be left with 2. Okay, so we have all of the 4 parts necessary. So this original integral, which represents u and dv, is going to turn into the other side of that formula. So we have u times v, which would be 2x times this e to the 4x over 4. I'm going to go ahead and pull the division of 4 out front as a coefficient. So if we take 2x times 1/4 e to the 4x, the 2 and the 1/4 would change to a half. We'd have x and then e to the 4x. And then we have to subtract the integral of v du. Kind of the opposite of the original integral we started with. So v was 1/4 e to the 4x. What is du? Go, Caitlin? 2 dx. Yep, you have to multiply that dx over. All right, so we still have an integral that we have to work backwards from, but this new integral should be easier for us to work backwards from than the original one we started with. If we clean it up a bit, we'll have 1/2 e to the 4x dx. So let's go ahead and think about, what did we have previously? Can we work backwards? Yeah. 1/8 e to the 4x. We don't know the bounds, so we'll use plus c. Okay? Again, if you're not sure, you can always take the derivative of your answer, and you should be left with the original integral. You might have to clean it up or simplify it a little bit, but it would eventually match that. Do we want to do that just to check it, or do you feel confident in your work? Do you feel confident? Okay. Eric feels confident. And you guys are confident in Eric. Okay. So by the transitive property, we're all good to go, right? Okay. All right. Let's check out the next one. Notice how we're multiplying two different functions together. Just by looking at it, we could find the derivative of at least one of them. We could work backwards from at least one of them. So this fits our by parts format. So we got to figure out what is dv. The leftover function would be u. And then we'll use those two pieces to figure out the other two that we need, the v and the du. So think about detail. What do you want to let dv represent? Do you have an exponential? No. Do you have a trig? No. Do you have an algebraic? Yes, that's x. Which means the natural log would be the u variable. So let's work backwards from dv to figure out v. And we're going to find the derivative of u to eventually get du. If you work backwards from x, what did you have previously? 1/2 x squared. And if you take the derivative of a natural log, 1/x, good. Okay, so there are 4 pieces. We're going to use those to help us rewrite the original integral. We need u times v. Order doesn't matter when you're multiplying, so if you want to do v times u, that's okay as well.